So, welcome back. We are going to look into droplet vaporization and then subsequently droplet combustion. Now, as I told in previous classes, this is very important. Okay, why? Because in all aero engine combustors essentially use liquid fuels like kerosene, different variants of jet fuels, and even the gas turbines, ramjets, scramjets, everybody, all of these engines and even afterburners want to use jet fuels, different variants of jet fuels in some form, and then this has to be burned. Of course, that is because of the large energy density. Now, how do you burn it? Okay, you cannot have direct combustion of the liquid itself. So, the liquid must evaporate, okay, and then it must be burnt. Now, at the same, you want the liquid to evaporate quickly also, okay, because you want fast burning of a lot of fuel in a lot of air. To quickly evaporate, if you have a pool like that, the surface area of that pool is not very large compared to its total volume. So, to increase the surface to volume ratio, it is best to have these droplets created, okay, small droplets. The smaller the droplet, the better is the surface to volume ratio. You can understand it clearly. It's like S by V is 4 pi r square divided by 4 pi r cube. So, it's proportional to 1 by r, right. So, smaller is the radius, the larger is the surface to volume ratio. So, one needs to have a very small droplets formed. And this can be created by a spray, but once this spray is created, once this droplet is formed, the question is that how does this droplets evaporate in a given hot environment. Of course, inside a gas turbine the temperature is high, of the order of about 700 Kelvin. So is same in a scramjet, the static temperature is pretty high. Of course, once again that comes out of thermodynamic reasons. The same reason why the pressure is high, the temperature must be high, because only when you add heat in this kind of environments you can add high pressure, and you can basically extract useful work. So, combustion happens in these air breathing engines in high pressure, and the incoming airflow is also at high temperature. All right. So, basically you are injecting a spray like this. You are essentially injecting if it is a say if it is a aircraft engine, if this is your say your combustor. This is the typical cross section of an annular combustor, and this is the solars, and this is your injectors. So, your liquid is injected like this, the spray is formed like this, where the air comes from like this when it is swirling, and the spray comes along like this, and then these sprays will break up and these droplets will form, okay. Different droplets of different sizes will form, and each of these droplets will essentially will undergo evaporation, and the method by which these droplets will undergo evaporation, the mechanism and the heat and mass transfer associated with it, that we will take up in this class. So, here you have a single droplet, and this is now my interface of the is a liquid air interface, which is the droplet radius, and we can say that at the droplet at this just above the droplet radius, my species mass fraction is Y1s, and the temperature is Ts, and of course the droplet is the droplet is the droplet is undergoing evaporation. In some cases it can also undergo condensation. So, when it is undergoing vaporization, this Y1s will diffuse out and it will go out, and this hot ambient has to supply the latent heat of evaporation. While it is condensing, the vapor has to essentially going in, and the heat of this is essentially going out, right. So, that is the thing, but in our case, for our interest, we will basically look into the droplet evaporation, and the ambient is at a species mass fraction is Y1 infinity, and its temperature is T infinity. So, as we said, that droplet dynamics vaporization combustion is the unique process in many natural and technological processes. Okay, it's not only this thing in terms of spray drying, in terms of like cooling. All this droplet evaporation is a very important phenomena that needs to be understood. So, spray, why we do not have a spray? Because spray increases the total surface liquid surface area for gasification. For example, spray painting, insecticide spraying, and spray combustion, which is a process of interest in a air breathing combustion engine. Okay, air breathing aero engine. So, the droplet processes and all these things like inkjet printing, raindrop formation, nanoparticle formation, and there are different things which are involved in droplet process. So, similar to the beaker problem, this we will consider the droplet evaporation problem, except that in this case we do not have Cartesian coordinates. We will choose spherical coordinates, but it is one dimensional, because essentially we will consider the symmetry in the we will consider the droplet to be axisymmetric, or we will consider the droplet to be symmetric in the azimuthal and the zenith plane, that is in the r theta coordinates, and we will only have r variation. So, this becomes a one dimensional problem. Okay. So, if it is a one dimensional problem, by applying continuity, we get ddr of r square rho u is equal to 0, and this gives a mass flow rate mv of this vapor to be essentially 4 pi r square rho u. We can say that this is, I mean, you can ask that where there are two phases, one is the droplet phase, one is the air phase. Why are we only considering mass flux of the vapor phase? This is because only this droplet is evaporating, it's going out, then there is no condensation of the air that is happening. As a result of this, we can say mv is equal to 4 pi r square times rho u, which is equal to constant. And then we can solve the species diffusion, the species conservation equation. Once again, you get this as the we essentially, this is the equation. This comes from the convective velocity, this comes from the diffusive velocity, and these two will give you the species velocity, and we can get integrate it, and just as we did it in the previous class for the beaker problem, and we will get the same thing, but here we have just used a non-dimensional mass mv, non-dimensional mass for it, that is mv tilde, and that is given by ln 1 plus bmv. Exactly similar form you will get, whereas bmv is a mass transfer number which is equal to 1 y 1 by 1 s minus 1 y1 infinity. That is, it's once again the potential for driving the evaporation in the droplet, and that is essentially the difference between the mass fraction at the surface and the mass fraction at infinity, and that is this is normalized by 1 minus y, the mass fraction at the surface. And of course, the normalization of the mass flow rate that we have done is essentially is equal to mv tilde is equal to mv, which is the actual mass flow rate, divided by 4 pi lambda by Cp Rs. Now, please pay attention to this particular normalization, because this will turn out handy when we do the d square law of droplet evaporation. Okay. Now, once again, this is not enough, because you do not know what your y1s is. So, this is even if you can solve for mv tilde, you do not know, because this is unsolved for why you do not know what y1s is, and that for to know what y1s is, you need the species, you need the energy conservation equation. This is reasonable, because you see that you cannot really solve the full problem just by the species diffusion, because ultimately the droplet is evaporating because somebody is supplying is the latent heat of vaporization, and the latent heat of vaporization is being supplied by the ambient. So, you have to consider the conduction and the convection processes that are involved to consider this latent heat of to close this problem, and that is why you need to, and that shows up in the fact that your y1s, that is the mass fraction at the surface, is not known, and that is why you need to solve this energy conservation relation, and that is what this yields. mv tilde is equal to nothing but 1 plus bhv, 1 plus this here heat transfer number, and the heat transfer number is Cpt infinity minus Ts. Now, one thing to note is that in both cases the heat transfer number, the mass transfer number in both the beaker problem as well as in the droplet problem, they do not change. That is, they are independent of geometry, and as a result they are universal. That is why they are basically universal numbers. Okay. So, if you once again write it in the dimensional form, you get this same type of relation, but of course here it changes a little bit. It is a 4 pi times lambda by Cp by times Rs divided by ln 1 plus bhv. and then the mass flux at the surface, then we can divide the mass flux by the mass flow rate divided by the droplet surface area from where the evaporation is taking place, and that once again comes back to the same thing, lambda by Cp di Rs. In the bigger problem it was L times L on 1 plus BHV. Okay. So now what we can do is that this is, so we have the, when this is also is equal to rho d by, as you see here, this is and this is of course in one important thing to note is that here we get even in this when we do the species conservation, the equation of mass flow rate that we get is mv divided by lambda by Cp. We can apply it here because we assume that lambda by Cp is essentially is equal to rho d, or in other words Lewis number is equal to 1. Okay. So because of that assumption we can assume that these two things are same, that is lambda by Cp is essentially is equal to rho d, and from now from the overall conservation of the droplet mass. Okay. Now what do we mean by that is that of course you have the let's go back a little bit. Now what I mean is that of course you have the full droplet, and now this droplet is giving out this vapor, that is essentially the droplet liquid phase of the droplet is converting to a to this vapor phase, and now while that is happening, since the liquid phase is being converted into the vapor phase, the droplet has to shrink, right, because the liquid mass of the droplet is basically becoming vapor and that is going outside. So this mass of the droplet has to reduce, and the volume of the droplet also has to reduce. So that means this is giving out this droplet is giving out this vapor flux. Okay. And for that it's this droplet has to shrink also. Okay. But of course this happens in such a manner that we can consider this while we do this analysis, we can while we do the analysis in the gas phase we can consider it to be in steady state, but now we can essentially write that the mv, that is the, we can equate that is the rate at which the vapor is leaving the droplet at the surface, that is the mass flow rate of this vapor at the surface, that is equal to the rate of change of the mass of the droplet itself, and that is the rate of change of the mass of the droplet at any particular time is given by 4/3 pi r cube time rho L, and that is the rate of change of that, and of course the minus sign comes because the droplet is shrinking. Okay. And so then we can write it in this form, but you see clearly here we have just done a small mathematical manipulation, that is or mathematical or jugglery, that is this 4 pi times rho L, we have just written this thing, that is d dt of Rs cube. We have written this in terms of Rs times dRs square dt. Of course there is a constant involved, right. So that we have written, and why we have written that, will become apparent in a very short amount of time. So now once you equate this thing, that is minus 2 pi rho L times Rs dRs square dt is equal to this thing, that is this guy. Okay. Which is nothing but 4 pi lambda by Cp Rs times ln of 1 plus Bv, that is 4 pi lambda by Cp times Rs times ln 1 plus Bhv. Okay. Or okay. Once you do that, as soon as you do that, then a few things cancel on both sides, and this you see this Rs cancels. So we get is essentially dRs square dt is equal to 2 times lambda by Cp divided by rho L times ln of 1 plus Bhv. Okay. and of course if we integrate this and we call this as the this droplet vaporization constant, which is k, because you see these are all constant for this particular problem, and then which this upon integration yields this thing, that is rs square is equal to rs0, that is this radius squared at any time t is equal to the rs radius rs of the droplet at time t0, that is the initial time, and that is given by this kvt, where there is a droplet vaporization constant kv times this time t. Okay. So essentially we can if we set this rs to be equal to 0, okay, this if we can set, that is the time it will complete vaporization, means this essentially should be goes to 0. So we get rs squared by kv is equal to the time for vaporization. So this is the very revealing thing, that is the total time for vaporization goes as rs square, or essentially it is a d square, that is a diameter square or the radius square. So this is the d square law, indicating that the vaporization time decreases quadratically with the droplet size, hence the principle of atomization. That is, if you so this is the thing, that the time scale or the time for the complete vaporization is essentially equal to the radius square, the initial radius of the droplet square, divided by the kv, the droplet vaporization constant. So the time changes quadratically. So larger droplet, more time, smaller droplet, less is the time. So if you can create a spray which atomizes into very small droplet, then it means that the spray will essentially become the fuel vapor cloud in a very short amount of time, and that is what is required, so that we can have proper mixing and we can have proper combustion with less soot, etc. And so this is the thing that we wanted to discuss. Now then we will finally, the topic is the d square law of droplet burning. So far we have discussed droplet vaporization. Now once we have the vaporization, we will apply the principles of the non-premix flame in the previous class to understand the droplet vaporization. So now here we have the droplet, okay. So now instead of and here you have the flame. So the flame is that, because here you essentially you can have oxidizers in the ambient, as you see here this contains y0 infinity t infinity. So this contains the oxidizer is in the ambient, okay, and this droplet evaporation is basically a droplet of fuel. So this droplet will provide the fuel vapor. This is the ambience contains oxidizer. So the fuel vapor and the oxidizer meet, and if you have a flame at this location at a certain standoff distance at a certain radius, that radius will be given by this RF, the flame radius. So this flame will basically conduct heat will provide heat through conduction in both the droplet as well as in the ambient. The droplet, the heat that it provides to the droplet will essentially help in sustaining the evaporation, because it will this flame is now going to provide the latent heat of evaporation required for the droplet to convert from this liquid phase to the gas phase. Okay. So this will work with the coupling function formulation, and the solution procedure will be similar to that of pure vaporization. So if you look into it, this will be the structure of the flame. So here you have the y, once again S means the surface of the droplet. Here you have the YFS, which will continuously now decay, because decay much faster, because it will be consumed completely at the flame. The temperature will increase from the droplet surface to the flame radius, because of course the flame is conducting heat, and then of course it will again decay on this sides because of conduction. So this side is the fuel side, this is the oxidizer side, and we assume that by the reaction sheet there is no fuel leakage on this side, there is no oxidizer leakage on this side, no oxidizer, and there is no fuel on this side, and also this will give also a profile something like this. So now we will just do straight to the coupling function formulation, but you should do it derive this by yourself also, and by the coupling function formulation it just becomes very simple. If you remember the coupling function, it's essentially beta I is equal to T tilde plus Y I tilde. T tilde, once again we apply the Lewis number equal to 1, and T tilde is essentially this stoichiometrically weighted CPT, and Y I tilde is the stoichiometrically weighted YF by YF0, stoichiometrically weighted mass fraction. And once you do the formulation, if you remember but just when we write it in the spherical coordinates, we just get this form. And now once again we can just simply integrate in the previous just as we did, but before that we can just write it in a normalized form, that is we can write it as R by RS. Okay, and then if we integrate, we get this forms once again. And now we have to apply the boundary conditions. It is exactly the similar way as we did it for the chambered flame. It is like the exactly like the chambered flame in but just in spherical coordinates. Okay, in spherical coordinates. So in the boundary conditions that we have to apply, and the boundary conditions are essentially at r is equal to infinity, that is here your y0 is equal to y0 infinity, which is fixed. Say if it is air, your y0 is fixed by the fact that the volume percentage is about 21% of oxygen. So this is that, if you convert that into mass fraction, this is the value that you get, some 0.20 something, etc. Yf0 should be equal to 0, yf tilde, because there is no reactant or there is no fuel leakage through the flame, and T tilde is equal to T infinity. Now similarly at R tilde is equal to 1, that is at the R by Rs is equal to 1. This is the boundary there. And then that is at this point basically this says that your MC, that is the mass rate of that is a normalized mass rate of evaporation, which is also the mass flow rate of combustion. The burning rate is SN times YOS. If we apply it for the oxidizer, that is exactly this oxidizer flow is exactly balanced by the diffusion, and there is no net flow of the oxidizer here, because there is no oxidizer condensation into the droplet that is happening. Then we will see that we will look into the we will look into this into the fuel. So but here there is on the right hand side you have the fuel vapor flux. So that is essentially is equal to the MC itself by before, as we have shown, because it's a balance between your bulk velocity and the diffusion molecular diffusion velocity, and which is essentially the species velocity times its corresponding density and all these things. So it becomes essentially the mass flux of the species, or the total mass flux of or the mass flux that is supporting the combustion that is being burnt. And of course we assume that the flux is for evaporation is supplied by conduction, and that is why it's dTdr is equal to MC times QV, and your T is equal to the T temperature at the surface. Okay. Now then we can solve for this coupling functions. We can solve for beta 0 and beta f, because your beta I is as we discussed here, is beta I is nothing but is nothing but your T tilde plus yi tilde. What beta I can be, it can be for fuel, it can be for oxidizer. Okay. So we solve for beta oxidizer, we solve for beta fuel, and then we apply the reaction sheet assumption, that is on the left hand side, that is at a smaller radius. Here there is no oxidizer, here there is no fuel, and as soon as you do that, we get the final solution, where again you get the exactly similar form. So these are the final solutions. Pay attention to this. So you get the we get this similar thing, that is MC tilde is essentially equal to your ln of 1 plus BHC. That is once again BHC is, if you remember, is the heat transfer number for combustion. So this is the heat transfer number for combustion. Previously was BHV, which was heat transfer number for evaporation. We will see exactly now what the difference is. The difference is essentially, you see that here this BHC involves of course this CPT infinity minus TS, which was also there in the heat transfer number for combustion for evaporation. But now you have this part, that is here your heat transfer number contains a very important this chemical heat release rate term, which is the QC, and this QC actually is now dominant over this guy. So, now the heat transfer is not actually coming from ambient. Of course, there is some heat transfer of the ambient, but now the bulk of the heat transfer that causes the droplet evaporation and then the combustion of this vapor is essentially this provided by QC, and this is normalized by the QV, that is the latent heat of evaporation. So, this QC is now this term is essentially much bigger than this term. So, mainly the droplet evaporation or the droplet vaporization is happening through the heat transfer, through the heat of that is applied by the flame that is situated at a standard distance of RF. So, then that can be estimated. This RF is an important parameter. What is the radius of the flame if we have a given the size of the droplet, and that is estimated by this once again from this reaction sheet assumptions, and we can get this by this formula, and once again we can get this temperature in an implicit form, where we show that this QC, that is this that is the heat of combustion, is now essentially the same things, that is 1 kg of yes, one of course 1 kg of, now this is, there is no fuel mixture because it is now purely droplet. So, so 1 kg of fuel now when you burn it, when essentially gives you, raises the temperature from Ts to Tf, and it raises the temperature from T infinity to Tf. Of course, these are the stoichiometric balances which shows that the burning is stoichiometric, but then it also is used for latent heat of evaporation. So, the same temperature is by the same argument, it is essentially the adiabatic flame temperature, but with consideration for the latent heat of evaporation. So, in this case the driving potential is BHC, as we have discussed before, that is for the driving the droplet evaporation or the droplet vaporizations, and the driving potential is BHC. It consists of an enthalpy term which is this guy, as we discussed, and this is much larger than the enthalpy term and the chemical term. The enthalpy term is actually this one, and this is the chemical term. So, the chemical term is actually much bigger than the enthalpy term, and which shows that in the case of droplet combustion, of course, if a flame around, then this flame gives much more heat, and as a result the droplet evaporation is much faster. Okay. So, in terms of normal droplet vaporization, and then as a result this BHC is of the order of 1 to 10, whereas this heat transfer number, the heat transfer number for combustion is out of the order of 1 to 10, whereas for the heat transfer number of vaporization is less than 1. So, it is a order of magnitude difference is there. And Tf is the adiabatic flame temperature of the system, allowing for latent heat of vaporization, as we discussed. The droplet temperature is close to the liquid boiling point and can be approximated it. However, it can be never reached due to the presence of products and inerts, and we can fold this problem back to the vaporization problem if we said y in 0 infinity that is equal to 0, and then of course it will lead to the RF to be equal to at infinity. Alright, so this using this once again we can relate the burning rate, that is that is MC is equal to 4 pi times lambda by Cp Rs times log of 1 plus BHC, droplet heat transfer due to combustion, add the flame to the vaporization rate, that is at the surface. So, essentially the droplet once again is shrinking because of its losing the mass because of the phase change of the liquid to vapor phase change, and then this vapor goes on to meet the oxidizer and then it burns. So, once again if we do the same thing, we can find out this if we set MV equal to MC, it is not assumption, it is a setting, that if you set MV equal to MC, and whereas MV is given by minus ddt of 4 pi r cube L, that is the rate of change of the mass of the droplet, which is a liquid, and this integration will essentially will give you there is some issue here. So, this what this integration will this just if we just can go back here, just to remove this. This is some problem with this thing. Then the this integration will essentially, we are essentially what we are doing here is that we are setting this MV to be is equal to mb equal to nc setting means that this guy minus ddt of 4/3 pi r cube L to be essentially 4 pi times lambda by Cp times ln of 1 plus BHC, right? Then we essentially, and as we know that we wrote this as Rs times dRs squared dt. So then we can write if mv is equal to minus 2 pi rho L times Rs times dRs squared dt, okay, and that is equal to 4 pi lambda by Cp ln of 1 plus BHC. And then this if we integrate this, okay, then what we find is that then if we just cancel these two things, pi is 2, and then we get dRs square dt is equal to lambda by there is Rs also here, yes. So this Rs and this Rs cancels, lambda by Cp times 1 by rho L, okay, minus ln of 1 plus BHC, okay. So now this is essentially constant, and if it is constant we can write this as once again the vaporization, which is exactly same as the droplet vaporization constant, but of course you note that this droplet the droplet heat transfer number, this is due to combustion, the previous one was due to vaporization. And then if we integrate this thing, Rs dRs square dt is equal to kV, then what this yields is nothing but this Rs square is equal to Rs 0 square minus kVt, whereas kV is given by 2 times lambda by Cp by rho L, that is the density of the liquid, ln of 1 plus BHC, okay. So now if we set once again that the total burning time to estimate, we set Rs is equal to 0, and then we get Rs square is equal to kV times tau c, therefore tau c is equal to Rs 0, that is the initial radius, by kV, okay. So this is what we get, that is a total burning time, or we write it as Kc, because this involves this here droplet because this involves this droplet heat transfer number for combustion. Then this is the total burning time, then we get it as this is the thing, whereas we can write that this is essentially is equal to Kc because it involves Kc. So this says we get the total burning time, tau c is equal to Rs square, the initial radius square divided by Kc. So once again you see that the total time is directly proportional to the radius square of the initial radius square of the droplet, of the initial diameter square of the droplet. It depends quadratically, okay. So that is the thing. Now of course you see that if you see that formula for Kc is essentially lambda by Cp times rho L, 1 ln of 1 plus BHC. Now if this is order of 1, if then we can just write this as, we can say that Kc is essentially proportional to this, if this guy is order 1, okay, because this guy is order 1 to 10, so ln of 1 plus BHC will be of the order of 1 essentially. So we can say that the Kc is essentially 2 times lambda by Cp by rho L, okay, and then we can set it as rho g times Tg is equal to this, and we can have an estimate of Kc in this form, okay. So just if we so find out the experimental observations. If we define this as the normalized radius RS by the initial radius, RF as the flame radius by the instantaneous flame front standoff ratio, and this is a non-dimensional flame radius, and the d square law prediction says that dRs squared dt should be equal to constant, then small rf tilde should be equal to constant, and capital RF should be monotonically decreasing, and small rf should be order of 1 for hydrocarbon in air. And actually we find that these laws are reasonably some of them are obeyed, and we find that dRs squared dt is much less than 1. RF tilde actually monotonically increases and is more prominent for low y0 tilde for fuel vapor accumulation, and this RF tilde, this normalized flame standoff ratio, flame standoff radius is essentially 5 to 10, which arises from which can be explained from the constant property assumptions. So with this we close today's class, and so we have covered a lot of grounds in the form of, we have studied a lot about non-premix flames. We used the coupling function formulation to see how today's and previous days class we have combined them to see how we have basically using the coupling function formulation one can explain the structure of a non-premix flame, one can obtain the burning flux, one can obtain the species profiles, one can obtain the temperature profiles, and most importantly we can find out that the flame temperature becomes essentially the adiabatic flame temperature for a non-premix flame, okay, for the given fuel air mixture, actually fuel mixture on the left hand side, air mixture on the right hand side. We have gone into look at standard evaporation of a liquid pool, and then found out on what parameters does this evaporation flux depend on. We have introduced the concept of droplet, or not droplet, but heat transfer number, mass transfer number, which emerges actually the driving potential for the evaporation flux, and larger this droplet mass transfer number, larger is the droplet heat transfer number, larger the evaporation fluxes are. And then we have also seen how both the species and the energy equation are required actually, and that is why these two numbers come to describe completely evaporation, and then sometimes we also need the thermodynamics, the Clausius-Clapeyron relation to find a relation between your species mass fraction or species mole fraction with the corresponding temperature. And then using these things and this concept we have gone on to describe droplet evaporation. We have found that the droplet evaporation has the time taken for a droplet to completely evaporate is essentially RS, that is the radius of the droplet, the radius of the initial droplet at the initial time squared divided by a constant called the droplet vaporization constant. We have seen that when you consider a flame droplet combustion, that is when if this liquid droplet is considered full with fuel vapor, once this evaporates, this fuel vapor can meet the oxidizer and we can have a flame. And then we have found that in this case the flame is actually the leading source for the heat required for the droplet evaporation. And then also we found that the time taken for the droplet to burn is actually also directly proportional to the RS square by Kc, whereas Kc here is the droplet combustion constant. So with that we just will close today's class, and then we will move on to non-premix flames. So thank you very much.